Hello my friends, welcome again to my video channel. Today we continue our work on the Kenwood TS130S. There are still problems with the contacts or with the switches. One set of switch we see here I took out and now they are cleaned and I will bring it in. I first had an idea to modify the switches to switch two levels in parallel, but it's not possible for all switches, so I don't do it. Makes no sense. A thorough cleaning is also enough. I did this, checked it with a continuity tester now, so I think it's okay. I still have to take out the other set, which is here, set of contact switches, to clean it again. I did it. I cleaned it, but it was obviously not enough. It's always difficult, such old switches. Maybe some of these switches have never been used or very seldom used, so it's necessary to clean them. Before we continue, short discussion. One of the viewers gave me the hint that these red dots here could be a proof that someone has repaired this transceiver and made some repairs. I know such stickers, but there should be a signature on it and a date. There is nothing. I checked it thoroughly. There is also no signature faded out over the years. There was no signature and only a red dot. Okay. This one here is where the two filters are, where we had the problem. Could be that someone realigned it some years, decades ago. The VFO had a very clean variable capacitor. The contacts were very clean, so maybe someone cleaned the contacts of the variable capacitor. These two red dots could be explained, but this one, no idea what it is. It's a power supply connection. The band switch is on the other side. Band switch is on this level here, not here. I don't know what this is for. So the red dots may tell us something. I really don't understand what it is. Anyhow, I will continue now with the switches. The switch is in place again. This is rather easy. There are only two screws. This set of switches here is installed differently. There are 4 screws from the front. Don't know why there is a different method. Maybe there's a reason that they can be moved a little bit vertically to adjust it in line with the front panel. Anyhow, I will clean it. Same procedure. And a small hint: when you have more than one switches to move, then you can do it this way. It's easier. Several times, and then clean it with a contact wash. Do not leave the contact cleaner alone, because these contact cleaners often dry out, get a little bit hard. This is too much for such small switches, so use a contact wash or gasoline, cleaning gasoline or similar like this. And now check again of the transmit function. We are on 7 MHz. As you can see, let's go a little bit down into the center. Carrier 0. The meter is switched to ALC mode. We have here the output power 40, 60, 80, and when it comes to 95 watt, the ALC starts. 95 watt is a specified output power for this transceiver. The ALC is set to 95 watt on the lower bands. Let's go to, for example, to 40 MHz. Same, okay, shows 100 watt. Let's go to 21 MHz. Same behavior. From a certain point the ALC reacts, it's 100 watt. And let's go to 28. The specified output power for 28 megahertz is 75, not 95, it's 75 watt. There's a separate setting for the ALC, and when we increase the output power we see, I should switch the send, we see that reaching 75 watts, 6, 7, 75, the ALC starts to react. That's okay. We can also have a look at the current, collector current. I think this is not correct. Oh, okay. "13 amps, the meter shows 18 amps. Okay, there is a difference. Maybe you have to realign it. But now the transmit function is also okay, and we can continue. And now it's time to realign the filter cores on the IF board, where we had the problem with this white powder. I think this white powder is oxide, maybe aluminium or tin or solder oxide, because it was obviously conductive. So I think it was due to a bad production process, not sufficient cleaning. Well, I insert feed in a signal on 14.250 with 0.25 microvolt, a very small signal. It's the limit of the sensitivity, and the cores here 1, 2, 3, 4, 5, 6 have to be aligned for maximum. This is the output of the AF loudspeaker. There's a dummy load, small dummy, and the scope is in parallel. I only use the scope to check whether there is some clipping. In the moment there is no clipping. Here we have clipping, so the output shouldn't be more than than 1 volt or so, 1 volt RMS. I align it a little bit slower, and then I peak all these cores for maximum. Wrong direction. This core was already maximum. The problem on the board was in this range here, so these cores here are obviously not affected. Okay, a little bit fuzzy work. Maybe I need a different alignment tool. Oh, this is better. So we are already on maximum. Okay, I will repeat it the second time to compensate some influences between the alignment points. Then this is done. Before aligning the oscillators, carrier and other oscillators, I check the supply voltages. They are okay within the limits of the specification. The counter is connected to the output of the carrier oscillator, but it's the audio frequency and generator filter that's the input. It has to be set in the mode. We are in the mode in the band 3.5 megahertz. In mode SSB, this frequency has to be 8.8285. 8.8285. Okay, I cannot align it precisely now. It is 0. when I go in the mode reverse, this frequency should be 8.8315. This is 300 Hertz, a little bit too high. I have to align it other direction. Okay, 83150. Okay, that's good enough. In mode CW, and in send, power is set to 0. Then I go to send. Frequency should be 8.83070. The 62 should be 70. Has to be adjusted with a pot. VR2. That's it. And the IF and now to check the IF shift, I press the set to 0. When I alternate between send and receive in mode SSB, the frequency should be 8.82850. Both, yes, that's okay. Eight to 8. This 49 should be 50. Okay. I think I have to realign it with VR1. That's the last pot at the end. Yes, that's it. This is 10 Hertz. The last digit is 10 Hertz. It's not relevant, not important. The S meter was okay, I checked it as we have seen before. Now checking the frequency accuracy. The signal generator is set to exactly 10 megahertz. The receiver here is set to 10.1 kilohertz above. I'm measuring the audio frequency. It is 1 kilohertz in reverse mode, and when I go to SSB mode and go 1 kilohertz below 10 megahertz, we again have 985. Okay. It is not absolutely symmetrical. I will adjust it with a trimmer on the side where the counter is, the counter unit. So I will try that we have here also 1 kilohertz, and then that we have the balance. That's the wrong tool. This should be approximately 1 kilohertz. Now I go into reverse mode and tune 1 kilohertz up. We have the same frequency. That's okay. Checking the read function. With the read I set it to 3.8. Then I switch the read off, and there's a pot. We can also align it to the same frequency. Oops. little bit fuzzy. Okay, that's it. That's not. Okay, this is also done. The next check is the balance of the transmit mixer. We have here a mixer, balanced mixer for the transmit path. We have here the transmit intermediate frequency, TIF, goes in. Here we have the VCO, goes also in, and it is mixed. Balancing transformer is mixed in this balanced mixer. Here we have a pot for the balance for the symmetry, and the output goes to this filter, goes back via this diode, and then it goes to this amplifier, to the driver and to the PA. And the task is now to have no input signal on transmit, to balance this mixer with this pot that there is no output signal, or nearly no output signal, as small as possible, and the rest is done by the filter. In the original alignment procedure, it's proposed to connect a RF voltmeter directly to the wiper. I think it's this one, this wiper, before it goes through the filter. I will do a different method. I connect the spectrum analyzer to the output of the transceiver, go to send and see what the signal is and the output. I will choose a high band, 28 megahertz or so, because in this high band the frequency is not highly damped, because the oscillator frequency, the VCO, is only 8.833 megahertz above the transmit signal. So when we have 28 megahertz band, the VCO is 36.8, and 36.8 is not so much attenuated in a 28 megahertz low pass filter. So I will check it at several bands and see that the frequency which comes in, the VCO, is attenuated as best as possible with this pot. This is a test setup. Output of the transceiver is connected to the input of the analyzer. Additionally, a small 10 dB attenuator to protect the analyzer. I hope this attenuator will be blown first, but I make sure that the output power is nearly zero. We're talking about fractions of a watt. Here we have the frequency, and then I will go to send in mode SSB. Here we have two signals, but let's have a closer look to it. We have a frequency of 28 megahertz. We have 5 megahertz per division, and this is 8.8 megahertz above. This is a VCO frequency, and here we have the frequency of the carrier oscillator. Should be 0, of course. This has also to be aligned down to 0 or as small as possible, and this one has to be aligned in the transmit mixer, as we have seen. And when I go to this pot, I can align it down to 0, not 0. This is rather minimum. And now I go to a different frequency, and we'll see, we will have a surprise. We are on 28 megahertz. I go down to 24. So we see this amplitude increases. And now I can optimize the frequency in this mode. Then we have here perfect minimum. I go down to 21 megahertz. Then we have here the minimum, go down to 14 megahertz. Nearly perfect minimum. But when I go to higher frequencies, you see the balance for different frequencies is different. It depends upon the fact that we have here only a trim pot. We should also have a trim capacitor to make it a little bit more broadband, this alignment, but we should know we are talking about milliwatts. This is 0 dBm plus 10 dB, it's 10 dBm, 10 dB by this alternator, 0 dBm minus 10 minus 20 dBm. This is 20 dB above, below, 20 dB below 1 milliwatt. This is not relevant. So I think we do not have a problem in practice. When it is below 1 milliwatt, the effect on the band is nearly zero. So I will optimize it on 14 megahertz as it is stated in the manual. And this is here. I think this is a good solution. It's for 10 megahertz, 7 megahertz, 3.8 nothing, 14, 18, 21, 28, 24 and 28, okay. And higher frequencies, the peak is a little bit higher. Maybe I should reduce it here in this bands a little bit more to get the best compromise. Okay, I think that's a good compromise. 28 a little bit too high. You see, whatever we do, but we are below, considerably below 1 milliwatt. The manual states minimum at 21 megahertz, so we go to 21 and then we should align it to minimum. (24, 28), okay. It is acceptable again. We are considerably below 1 milliwatt. 10 milliwatt, 1 milliwatt, 0 to 1 milliwatt, so no further action required. Next topic is the carrier suppression on 14 megahertz. We are here on 14 megahertz. This is a carrier. I have no modulation. Microphone gain mode SSB. Microphone gain is set down to 0. Just to check when I increase the microphone gain. Okay, a little bit of change, but this carrier has to be minimized with the carrier balance. There are two items, a resistor, a trim pot and a capacitor. First to check the resistor. Okay, it is optimized. And then the capacitor, the trim cap. What's this? Do I have a problem? Now there's the slot. Sorry. It was optimized. Yes. Again, we have here 10 milliwatt, 1 milliwatt, 0.1 milliwatt. So I don't think that this is a problem and we can accept this. And now the last step of my checks is the setting of the ammeter collector current. I tempered a little bit with it, so I have to align it now. The procedure in the manual is rather difficult. It makes it necessary to open the PA unit again, unsolder some wires, the plus supply, connect an ammeter into it and then align it with with this ammeter and with the trimmer, so that we have here equal indication. I don't do this. I do an easier way, because this is not a very precise meter, it's only an indication. I will measure the current. Mode transmit, CW, carrier is 0, no output signal. Then we have a current of 1.5 amp flowing into the transceiver, and then I increase the output power until I have 10 amp more, and these 10 amp more are the collector current of the PA. Maybe the driver current also has to be taken into consideration. So when I have here 10 amp more, I will have here, for example, 9 amp more or so. Let's check where we are. I increase the, we had, sorry, 1.5. Then I go to 10, 11.5. And this should be an indication of 10 amp. We have a little bit less. I go to the trimmer. Now I have 10 amp. I think this is okay. When I further increase the output power up to 100 watt, we have 16, and we have an indication of a little bit less than 15. That's okay. And now a short test of the modulation, first with the microphone in mode SSB. We are on 20 meter band. When I go to transmit, there's the ALC. I can increase the microphone gain. We have more ALC. Output power is 30-40 watts. With a speech processor, it is a little bit more, but not considerably more. Okay, I think it's a rather simple processor, which is not very effective. Now let's check the Vox function. Vox is in. Okay, transmit, you see it. Time delay is anyway here one of these pots. That's not important. And now we will check CW. Now CW mode. And I go to send. Without send, we have the CW monitor. When we go to send, we can have the output signal. This is collector current. When we go to ALC, and now with Vox function, which is now key operated relay, not a voice operated relay. You see the frequency jumps between CW receive and transmit. And we have okay, it's 800 Hertz difference. You see, receive, transmit. There is a shift needed for the beat frequency. That's it. These modes are also okay. The last check is the characteristic of the bandpass filters. On the RF unit, these bandpass filters are used for RX and TX mode. To check it, we have one connection. That's the output of the network tester from the local oscillator. This goes here to this pin. This is a VCO, this is a PLL unit. And the output of the PLL unit is a VCO, which goes to the RF unit. And the output of the RF unit, which goes normally to the power amplifier, to the driver. It is unplugged, and this is connected to the detector. It's a logarithmic detector based on an AED something, I don't know, it's an analog devices detector with a logarithmic or dB characteristic. First is the 3.5 megahertz band. You see it is set, and we have here the resulting characteristic. It's very close to the specified characteristic. Let's have a thorough look at it. It is not stated which impedance the detector and the generator should have, but I think the 50 ohm system is okay, because they are the input of the RF unit is low ohmic and the output of the driver also, so I think it's good. That's the 80 meter band. We have here 3.5 megahertz, 3.4, 3.8 up to 4 megahertz. The ripple should be less than what I was saying, less than 5 dB. A little bit difficult. We have a 10 dB per division, so from here to here we have 10 dB, but they don't say whether it is plus minus 5 dB or whether it is 5 dB maximum to minimum. And we have a 4 megahertz. For European applications, I could try to shift this frequency a little bit down to get a less ripple, and to increase this to 3.5 megahertz and 3.8. We are here, but this is a little bit too high with 4.1. The characteristic says this when you see the picture in the manual, but I do not touch it. I don't see any reasons in the moment, because some dB more or less in the 80 meter bands. The problem is not the level, the problem is a crowded band. Let's go to the next band. For the 7 megahertz band, we have here 7 megahertz, 7.5, 7.2 for European bands. It could be also possible to shift it together, so to make it more flat on the top. The ripple should be less than 2 dB. You also have here more than 5 dB from here to here, but this is due to the wideband setting. When you make the setting a little bit smaller, less bandwidth, then the top could be flattened. But again, I don't do it. Could be only a reason to reduce the influence of strong broadcast stations above 7200, but nowadays we don't have strong broadcast stations, so it's not a problem. So I think this this is also okay. Here we have the 10 megahertz band, 10.1, 10.15, so the filter is much more broader than necessary. Could be, I think, made a little bit smaller, could be aligned to a smaller setting, but it's not relevant. I don't change it also. This is 14 megahertz, 14.0, 14.5. You see also a very broad band. Special functions are also included. A little bit lower frequencies for, I think, military operation or so, as it was in the early days. This is 18 megahertz or 17 meter. This is very close to the required characteristic. 18.125 is exactly here in the center where we have the drop. It's a little bit strange, but it is as it is, and it should be so as it is according to the manual. Okay. This is 21 megahertz or 50 meter. It's also very close to this picture. There's a band 21 and the upper band and 21 450. That's also in line with the manual. There is a 12 meter band. We see here 24, what it should be. It's also in line with this. A little bit more frequency, but the top is flat, as it should be. And the last one is 10 meter band, 28 to 30 megahertz, or 28, 29.8. Flat top. This is also in line with this here, with this picture. Sorry, with this picture. Well, that's it. In general, the alignment in the band, in the lower band, is a little bit too broad. Could be made more narrow, I think. But it's a question of the coupling of the resonant circuits. Maybe the coupling is a little bit too strong, so the circuits get broader. Then it would have to be optimized, the coupling and the tuning of each circuit. I don't do it, I leave it as it is. We can work with it, there is no absolute error. By the way, 10 meter band has 3 settings. When you switch to the next step, and the other step, the next step, there is no change in this characteristic, of course. We have 3 times the same bandwidth. Sorry, this is the wrong one. This is the right one. 1, 2, 3. Well, that's it. Just to clarify the impedances when aligning it, the proposed circuit for adjustment of transmit bandpass filter is 33 ohms and the diode rectifier to the oscilloscope. I have here a detector unit, logarithmic detector with 50 ohms input. It goes to the coil pack, but not directly to the coil pack. It is connected to the output of an amplifier, and the output of the generator, of the sweep generator, is also not connected directly to the coils. It's connected via the transmit mixer. I show in the schematic. We have here the RF unit, the sweeper output. The generator was connected to this pin, VCO. It went through this mixer. The mixer in this case is only an amplifier, symmetrical amplifier. The output goes through this capacitor, this diode, switch, band switch, back through this diode, to this amplifier, sorry, from the switch to this amplifier, and then it goes to the drive output. So we have here 3 transistors in series, impedance converter, so it is not relevant whether we have here 33 ohm or 50 ohm. Also the impedance of the generator has no influence on the band filter, because there are always some transistors between, so the impedance has no influence. The transceiver is ready now. Everything is checked what should have been checked. Of course, I didn't a complete realignment. I think it's not necessary. I didn't find any problems which are indications that there's something wrong inside. The parameters are okay. This hole here, which is protected by a rubber cover, is the trim capacitor on the counterboard to set 0 beat with WWV signal, the 10 megahertz signal, or another external reference signal to calibrate the frequency counter. That's it. Now we can focus on the digital frequency controller. The DFC230 looks also a little bit dirty. Someone glued some green felt on it as a protective for the other equipment. The rubber feet seems not to be original, but doesn't matter. I leave it as it is. That's not a problem. The whole case needs some cleaning. I think I will do the same as I did with the transceiver. Here we had a problem. I think we discussed about it, that there is a damage. I don't know whether it slipped out or whether it is broken. There is still some black. It is broken simply. The problem is that these These plastic cables sometimes have a problem with the isolation. This isolation has sometimes a tendency to shrink, to become shorter over the decades, and copper does not shrink. So the copper wires here still have the original length, but here we have some problems, so I think I have to cut it here or so. There's enough length. I don't know why it is such long. Maybe it is thought to have here a remote control unit to place the transceiver anywhere, just to control the frequency from remote. So first I have to do this. The other cable seems to be okay, also a little bit dirty. First step is to open and to clean it and to look for some modifications. I don't see any hints in the manual that there are modifications, but I'm not sure. We will open it and we will see. I took away the cover and the top and the bottom cover, the knob, two knobs. I only can remove the protective cover of the display. That's rather easy, only one screw. And I can clean it, but the rest cannot be unmounted so easily. There are 4 screws on the side, but then the whole plastic unit, the whole front panel comes out, and the display and the encoder is set is connected to the front with some screws from the rear side. So when I want to unmount the whole unit, I have to remove some screws, and it's difficult to get it rebuilt. So I don't do it. I can clean it from the front as it is, no problem, with some wet paper and some small brush or so, and the knob, both knobs in the front, and this plastic cover I will do in lukewarm water with some soap. That's sufficient, and the top cover and the other bottom cover I can clean also same way. I pinched off the microphone cable some centimeters behind the connector. The microphone connector is repaired, it's in place. The frequency controller is connected to the transceiver. In the moment we have the mode that the transceiver is controlled by the internal VFO, both receive and transmit. 1, 2, 3. A little bit more, 1, 2, 3. When I go to receive, this controls the receiver. You will see the frequency jumps up, 150, but in case of transmit it goes back to the VFO. When I switch also the transmit to the remote, then we have both receive and transmit, and I also can of course work in receive with this frequency from the VFO. In the case of transmit, this one is active. This works. There's some read function. Okay, but the read function follows. Sorry. Transmit, receive with read. When I switch with read off. Also okay, memories I will check later, but as you see they are also good. This unit works. I only will check the accuracy of the frequency. There's internal crystal oscillator, reference oscillator. I will check it with my frequency counter. And this will be the last step of my work on this line. The alignment of the reference oscillator, which is here with this crystal, is done at test or checkpoint 1, connected to the counter, 5 MHz, and in mode CW, in receive mode. This trimmer TC1 should be set to exactly 5 MHz, and in mode transmit this frequency should be 700 Hz up, and you should have here a 7, not 60, not 610, should be 700 with the second trimmer. Does not react. Nice, nice, or not nice. This trimmer is obviously dead. Now I got it. Receive and transmit. I think the function is reverse. I have to check the schematic. Which trimmer is for what? Ah, now I see. TC2 is this one. And on the schematic this is labeled as TC1. Another error in the manual. In the drawing these two trimmers are swapped. Ugly, ugly, but now it's okay. Receive. You can use TC1 again. This is for receive. This is transmit. Receive, transmit. Okay, now it fits. There are some typing errors in these manuals, in the service instructions. I found a mismatch regarding clockwise and counterclockwise and so on. So be always careful. Typing errors, decimal dots are missing and so. These service manuals are not very thoroughly checked. They are written and then printed, and the quality could be better. So thinking is always necessary. And the real final work is cleaning this relay. It's a one-pole switch-over relay used for the mode receive, transmit, main or remote. It controls these switches. I did it with a small strip of blotting paper. Now it's okay. I removed this plug. Now we can close it. And now we are at the end of the project with this Kenwood TS130S and the frequency controller DFC230. We had mainly three problems with contacts. As I always say, contacts in the switches, contacts in the pots, and contacts in the relays. The bulbs were replaced by LEDs. A modification was removed here from the microphone. On one pin there was 13.8 volt. Luckily there was a fuse inside. Some alignment checks regarding S meter and collector current, but the rest is okay. There's another modification I've seen. This microphone MC30S from Kenwood. It has in the original version a lever between the switch between noise cancellation and normal. Someone replaced it with two knobs, frequency up and down, and you see we can tune it up and down in frequency. Okay, not bad. I leave it as it is. Not necessary to unmodify it. Hope you enjoyed this little series about this transceiver. There are other projects here in my pipeline, but this was a small summer project, not so challenging. It was nice. Stay tuned, stay healthy, and see you on this channel.